Welcome to the podcast Interferometry and Excellence. In this podcast, I talk to various experts about applications of interferometry in the cluster of excellence quantum frontiers. Today, I would like to welcome Dr. Wu. He is a scientist at the Albert Einstein Institute and leader of the topical groups Substandard Quantum Limit in Suspended Interferometers. First, I would like to know, what is the research focus of this topical group?
Yeah, so our research group, the name is a little bit complicated, yes, so we can break it up. Substandard quantum limit shows that we are interested in researching ways to overcome the standard quantum limit, a limit imposed by quantum mechanics on how well you can measure things. In suspended interferometry means that we want to use mirrors which are held up by wires so that they are inertial test masses. And the reason for this is because we are interested in using these techniques to improve gravitational wave detectors. And in order to do all this research, what we have set up is what we call the AEI 10-meter prototype facility. And here in this facility, we're building a mini gravitational wave detector, so 10 meters long. It's not designed to detect gravitational waves, but to really focus on prototyping new technologies and test new techniques to improve gravitational wave detectors, with a focus on quantum noise.
And what is the so-called AEI 10-meter prototype?
So the AEI 10-meter prototype is the name which we call our entire laboratory. This includes the main part of it, which is a large vacuum system. Large in the sense compared to a tabletop, it's 10 meters long. It is a Michelson type interferometer, so it has an L-shaped, and each one of those arms is 10 meters long. So in total it will be 20 meters long, but it is a Michelson interferometer. And inside this vacuum system, we then have all our optics, our mirrors that we use as test masses, for example, and the beam splitter, which is used for the interferometer. All this goes inside that vacuum system, and that's where we're building what we're calling the sub-SQL interferometer, which is an interferometer specifically designed to be first limited by quantum noise, so that we can then test ways to overcome the quantum noise to make it even better than what quantum mechanics, the standard quantum limit, says we can measure.
And what are the goals of the prototype?
So as I mentioned, our main goal, so our first and foremost focus, is to be a prototyping facility for gravitational wave detectors. That's why we're building this kind of mini gravitational wave detector. Yeah. I say mini here because 10 meters is big, but compared to the, for example, 4 kilometers at Advanced LIGO, it's much, much smaller. Yeah. That's also the important role which we play. It's also important that when people come up with new ideas for gravitational wave detectors, a lot of the time they demonstrate it in their own labs. And here they usually do experiments on very small scales, on like a tabletop, which is not exactly the same as doing it on a 4-kilometer scale. And so we also feel the very important role to show that you can scale up your tabletop experiment to something which is similar, very similar to a proper gravitational wave detector.
What is the advantage of a prototype facility?
So the advantages of a prototype facility is the fact that we can do tests which are very similar to a gravitational wave detector. Unfortunately, for a real large-scale gravitational wave detector like Advanced LIGO or Advanced Virgo, they can't afford to shut down the entire interferometer in order to test out new technologies and do experiments. Their main job is to observe the sky and look for gravitational waves. And so that's the important role which we play. We are a facility where we can easily shut down the system, try out new things, change optics, change experiments. We can perform all these tests because we're not trying to detect gravitational waves. We are specifically there to test new techniques. And a lot of the times when people do experiments to come up with new ideas for gravitational wave detectors, they usually start off doing small experiments on tabletops with small optics, small distances, and it's not always obvious that these experiments can scale up to the large-scale detectors. And so that's why we also have these prototype facilities to demonstrate that these ideas and these small experiments also work with bigger experiments, which are almost the same as a full gravitational wave detector.
You have just mentioned quantum noise. Maybe you can tell us, what is quantum noise?
So quantum noise is the idea that, everywhere around us, in all of space, in all of the vacuum, there exists these little fluctuations which are described by quantum mechanics. We call this the vacuum fluctuations or the vacuum noise. Be careful here, when we say vacuum, we're not referring to our vacuum system, but rather the empty space, the emptiness that is around us. It's the idea that no matter where you are in the universe, there is always, even if you don't have air, you don't have a planet or anything, you always have this little bit of noise there. And this is what we call quantum noise. These little fluctuations in our interferometer, they start to interact with the light as well. And so your light, even though it's coming as, if you think of your light as photons, should be coming from a laser at very regular intervals, so that you have one photon hitting, for example, every 1 second or something. These quantum fluctuations start to interact with these photons, and so it makes it a little bit more random again. And it always creates this noise that is always present whenever you try to measure any type of light. For example, the light from an interferometer.
How does quantum noise lead to the SQL standard quantum limit?
Yeah, so the idea of the standard quantum limit, in particular for interferometry, is the idea that when you try to measure harder, so you try to improve your signal compared to your quantum noise, unfortunately you also suffer from what we call back action noise. And this is the effect that the system kind of fights against you and doesn't let you measure harder. And this is another way of really describing what is known as Heisenberg's uncertainty principle. Yeah, if you try to measure two quantities, it's not always possible to measure them with extreme precision. For example, in our suspended interferometers, what we're really trying to measure is the position of the mirrors in our interferometer. And of course, when a gravitational wave passes, it stretches space-time, and so it looks like the position of the mirrors have changed. Now, one way to improve that quantum noise is to use more laser power to inject more light into your interferometer, and that will improve your quantum noise at your photodetector when you try to measure things. But unfortunately, light also carries some momentum with it, and so it can actually start to interact with the mirrors themselves, and especially because these mirrors are suspended, so they're kind of floating in the air, just held on by wires. When we inject more light in, of course there's still quantum noise on that light, and because now your light is randomly changing inside the interferometer, it also starts to randomly push on your mirror. It's the light itself with the quantum noise which pushes on the mirror. And so injecting more light, yes, it helps you beat the quantum noise which you measure at the photodetector, what we call shot noise, but then it starts to push against the mirror and actually cause a motion which disrupts your measurement again. And this is what we call the back action noise, or the quantum radiation pressure noise. And it's the interaction of these two noise sources which says there's a limit for how well you can measure by just changing the optical power. So the standard way of trying to reduce quantum noise, that you can't just constantly increase power, but you run into this back action noise.
So we can't exceed the limit.
No, that's not quite true. The name is a little bit deceiving there. It's not a fundamental limit. It's a limit that is imposed by the standard way of trying to decrease quantum noise, which is, in our case here, trying to increase the optical power into the interferometer. And again, this is an idea of Heisenberg's uncertainty principle, which says you can't measure two quantities with extreme precision. And in this case, it was momentum, so the mirror actually moving, versus its position. But what if we change Heisenberg's uncertainty principle a little bit? It says we can't measure both of them at the same time with infinite precision, but we can make one much worse and make one much better. So we trade off one against the other. And this is where the idea of squeezed light also comes in. This is a technology which the Albert Einstein Institute, which I work at, had a long history of developing this idea for use in gravitational wave detectors. And here, instead of just letting nothing go into the interferometer, they actually inject a little bit of what they call squeezed light. And this is no longer kind of random vacuum fluctuations which go into the interferometer, but kind of well-defined source of light, which has a lot of uncertainty in, for example, its amplitude, but then has a very low uncertainty, so a low amount of noise in its phase, which is what the interferometer is trying to measure.
Have you overcome the SQL yet? Or is it only theory?
So in the prototype, so in my group, we have not actually done this yet. We are still actually setting up our interferometer, so it's not even possible at the moment. But our community, so our colleagues, for example, at Advanced LIGO, have shown that by using this squeezed light, they can also, first of all, reduce the shot noise, but that doesn't really surpass the standard quantum limit. It's kind of the same as increasing your optical power without actually increasing it. But what the colleagues at Advanced LIGO did is they changed the uncertainty such that there is a little bit of uncertainty. There is less uncertainty also in the kind of amplitude, so to say, of the laser light. And so they were actually able to cancel out some of this back action noise, which I was describing. And that is then a demonstration of actually beating the standard quantum limit.
What are your personal goals in this field?
Yeah, so personally, my interest in this field completely stems from the ability to measure things more and more precisely. My research interest since I finished my undergraduate studies was always to improve metrology and try to make instruments which can do the best that they can. The astrophysics and the gravitational wave side of it is interesting, of course, but for me it's not my main driver for my research. So my personal goals is really to make the most sensitive instrument which I can and improve the field from that side.
Yes, very good. So, thank you for the interview.
Okay, thank you.